Finally, the fourth of our four segments. Well, actually, we're going to use a little bit of the third segment here because I skipped right over some of the real-life applications that we need to look at today. Okay, so right triangle trig, we're about to finish up this unit. We know all 6 of the trig functions. We know how to use the unit circle. We can use our calculator. This we have really focused on. I hope not to the exclusion of this. We will be emphasizing this in the future. We know the difference between a reciprocal of a trig function and the inverse. For the reciprocal, we use this key, and for inverse, we use these keys. We know how to solve right triangles, and we have been working on perseverance. We're going to continue with this today with the real-life applications of this. Trigonometry is used in all sorts of real-life situations. You may yourself find that this is helpful to you in real life, even if you never have a career in it. Real life applications where we're going to spend some time here for a moment. Guidelines for solving a triangle problem. So let's go through what the process usually looks at. One of the things we know about real life applications is that each one is a little different from the other. But we're going to categorize them. At least for today, we have, I think, 3 main types that we're going to look at. And for any of these triangle problems, draw a sketch. And you might want to make it large. Sometimes I make mine too small, but draw a sketch. So that's the first thing that you're going to do. Then look for right triangles. So in your problem, look for something which implies a 90-degree angle. Now this, in real life, sometimes the ground is not perfectly level and the trees do not grow perpendicular to the ground. But in our problems, we're going to simplify things a little bit. We're going to assume, unless said otherwise, that the ground is perfectly level and a tree or building, it will not be the Leaning Tower of Pisa unless it says so. The building is perpendicular to the ground. So do find right triangles wherever you can. You can even invent them in certain situations. Mark the known sides. Okay, there'll be some information that's given. Mark that information. With this, you'll have actual values. And here you're going to be using variables to mark the unknowns. Express the desired sides or angles in terms of trig functions. And you'll know which function to use based upon which quantities have been given, which are the knowns. Finally, solve that trig equation you generated and express your answer using correct units. While we're talking about units, make sure back here with your known that those units are consistent with one another. Now, one of the things that doesn't need to be mentioned here, because we all know it so well, watch out for mode. If you're working with degrees, make sure your calculator is in the degree mode. Okay, here are two problems I skipped over. You had a mess of surveying problems in segment 3. You also had some of this type of problem, elevation and depression. So we'll want to do one of those, and what I meant to focus on, and we will focus on somewhat, in this segment was bearing and course. So back to surveying. I'm standing at point A on one side of a river. Oh, a river. Maybe I'd like to use a blue. Okay, so I have a river passing by, and I'm standing on one side of it. Okay, so let's say I'm right here, point A. There's point A. And I wish to measure the distance across a river to a house at point H on the other side. I should have made my river longer. Just a moment. Yeah, one of the things about the sketch, I want to make sure it is big enough. So, notice I'm choosing a flat section of the river. And the other thing I might want to do for this problem is the point A, I might want it to be right on the riverbank. Yes, I'm going to make my point A right on the riverbank, right there, A. And I walk 50 feet along the riverbank to where the house is. Let's see, we'll put the house right here. It's a little house. That's my house. Back here. So I walk along the riverbank to a point right opposite the river. Right opposite the house. Point A on one side of the river, and wish to measure the distance across to a house at point H. Okay, so this house needs to be called point H. And I walk to point B. And I measure the angle A E H. Oh. So it's so important to understand what the problem is asking you. How am I going to fix this? Because what I understand is ABH, the way I have understood the problem, this is a right angle. It couldn't possibly be 1823. I'm standing at point A, and I wish to measure the distance across a river to a house at point H. So obviously now I understand that the house is opposite point A, not opposite point B. Well, okay, I can learn. I'm going to want to move this house. Let's see if I can grab it here. I'm going to move this house. The problem is saying the house is opposite over here. Now I can put point H. Where it belongs. This is point B. This is point H. What do I know? I have some distances that I know. This distance here is 50 feet. I'm told that I measure this angle and it's 18 degrees 23 minutes. That's angle ABH. You remember that from geometry. B is always your vertex, the one in the middle. So I'm going to call this a right angle, and this one right here is 18 degrees 23 minutes. The one that I'm interested in is this one here. I'm going to call that Y, the vertical, opposite the angle I have measured. That's good. So what would be the right ratio for me to use? Notice I'm not interested, nor do I have any information about the hypotenuse. Whenever the hypotenuse is thrown out of the equation here, you know you're going to be working with tangent. Now, I could use cotangent, but why would I, since my calculator requires me to use tangent first. So I'm going to express this in terms of tangent. My equation is the tangent of the angle I know is equal to the length of the side opposite that angle, my y, which I don't know, divided by the length of the leg adjacent, which is 50. So my y is going to be 50 times, okay, let's pull over the calculator. See how you cannot actually get through this course without having your calculator available at almost all times, because this certainly isn't one of the special triangles. We're not going to be able to figure this one out on our own. So degree mode, and I have to hit that enter, it's not going to stick. And now I want tangent, oops, clear, tangent of 18 degrees, 18, I know where to find degrees, and 23 minutes. And minutes can be found there as well. Close my parentheses, which I don't need to do. Seems neat. And I've got 3, 3, 2, 3. Always go to at least those 4. 3, 2, excuse me, 3, 3, 3, 3, 2, 3. And we're going to multiply that times 50 times 50, 16.62. So the distance is 16.62. And what are the units we're working with here for distance? Feet. You are not done until you put those units in, if you have them. Okay. So that's an example of a surveying problem. I'm not going to do number 18. You've probably done both of these already anyway. Then there is angle of elevation and depression. We have so many instances where we're interested in this. As a person looks up, okay, person at point A looks up at point B, an angle of elevation with the ground, that should be an is created, right? It's right here. I'm standing here, assuming the ground is nice and level here, and I create an angle of elevation. When B looks down at point A, so if I have somebody up here, perhaps looking out the window of the building, looking down at me down here at point A, they have an angle of depression created with a horizontal line. If whoever's here looking out the window looks straight ahead, they form a horizontal line with their angle of view. And if they look down to the ground, we have an angle of depression. The angles in this case are congruent. Why is this? Anybody remember? These two lines are parallel. And what do we call a line that intersects parallel lines? I've got two, I'm sorry, I can't even draw a straight line. Two parallel lines, and if you intersect that with another line, this is a transversal. Remember all this from way back in geometry? And transversals create congruent angles with the parallel lines. That is important for us to remember. Bearing and course. When ships or planes navigate, okay, we're going to spend most of our time on this. They need to have a simple way of explaining in what direction they're traveling. How are they going to communicate this? One way they do that is bearing. The bearing is always in the form of north or south at an angle east or west. So we think of bearing, we're always thinking of north or south. A bearing is always drawn from the nearest north or south line. A heading, of course, is always drawn from the north line in a clockwise direction. Following our ship's direction, the bearing and the course. Okay. So the bearing, remember what we said? It's always north or south. So in this case, the ship is not heading south, it's heading north, and it's not going west of that perfect north, it's going east of it. So its bearing is north, 60 degrees east. So that's saying it's going 60 degrees east of perfect north. Its course is 60 degrees. And this one, the ship is not headed northward, it's headed southward. So its bearing is south, and it's not headed to the west or south, it's headed east. Its bearing is south, and it's 70 degrees east. So the one we're going to pay attention to, even though the one we're given is relative to the east-west line, we're always going to express it relative to north-south. So we know these are complementary, this one has to be 70 degrees, and that's what we give. My computer does not like me making little degree signs. And what is my course? Remember, a heading is always drawn from the north line in a clockwise direction. So let me change pen colors here. So here's north line, and we're always going to go in a clockwise direction. So there it is. And that's 90 degrees plus 20, so it's 110 degrees. Now, one thing may be a little confusing to you here because we've already learned that when you go clockwise in trig, yes, it's a negative angle. But when we're talking in a real-life application, if you're a sailor out there, you're not giving negative angles. And clockwise is the most convenient way for us to think about things because our clocks travel in a clockwise direction. We're so familiar with that. And of course, all of this was developed before they even had such a thing as a digital clock. So it's 110 degrees is our course. The next one, again, we're headed southward. This time we are headed towards the west. So our bearing is going to be south. And notice the angle given is relative to the north-south line. South 35 degrees west. And our course, it's 180 degrees plus 35. There it is. This one, we're headed north, and we're going west of north, so it's north, 72 degrees, 18 minutes west. That's our bearing. And our course, remember, we always go clockwise from north. So our bearing is going to be 90, 180, 270 plus whatever this is. What is this little piece right here? It's 90 degrees. Or how else could I express that? I could express it as 89 degrees and 60 minutes minus 72 degrees and 18 minutes. So this will be 42 minutes, and this will be 17. So we 17 degrees. So we add that on to 270 degrees. And that's how we get our course. Here's a tip for you to use in these bearing and course problems. When you see or you're asked for a bearing or a heading, always look for the word from and draw the XY axis at that point. Okay, so from is the origin. That's where you are, that's the from. If the bearing from A to B is north 65 degrees east, so let's draw that one. So I'm right here. That's my from. If the bearing from A to B is north, okay, so we're going to be in one of these, and it's east, and it's east 65, then my 65 would be right here. This would be my 65. Then, when I'm coming back the other way, the bearing from, okay, I should mark points, shouldn't I? Make this problem understandable. Here's A, and here's B. But if we're going the opposite direction, now my B is right here. And remember, it's going to still be in exactly the same line, but just in the opposite direction, right? So we're headed here. And now I've got 65 degrees here. Whoop. And now the bearing is south, 65 west. Okay, so notice that. Opposite. This was going north, this one's going south. Just what you'd expect, right? Opposite. This one was going east, this one goes west. These we're actually going to spend a little time going over at least one of them. Maybe 2 or 3 or 4. I don't think we'll have time for that. Okay, a Jeep leaves its present position and travels. Okay, so I've got the Jeep right at this point here, the origin. It's headed north with a bearing, there it is. So this is 62 degrees right in here. I really didn't draw that to scale well, did I? For 29 miles. Okay, so it's going from here to here, and this distance along this ray is 29 miles. How far north and west of its original position is it? So let me draw that. I have, here's my north line. This was 62 degrees. And this is a right angle, so this has to be 28 degrees, doesn't it? Well, you know, I don't mind being out of scale, but that's a wee bit too much out of scale. And it, of course, was originated over here. 62 degrees would look much more like this. So let me get it right. 62 degrees is this angle right here. Now, I don't want to take up too much space with that. So I go to this point here, from this point here, 29. I want to draw a triangle to show me how far north and west of its original position it's at. So this is, believe it or not, right angle. I don't know, I'm not satisfied. This is 29. See if I can get myself to draw straight here. No, that's not straight either. 29. That's better. Hopefully you draw better than I do. Okay, so this we know is 29. This we know is, so this was the distance. What is this angle here? If this is 62, these are complementary, this must be 28 degrees. Hates it when I do little circles for some reason. So I'm interested in knowing this distance here, how far north and how far west. And I have the hypotenuse, so this tells me I better be using sine. I'll start by finding the one opposite, which will be in my sine ratio. The sine of 28 degrees equals how far I've traveled north over the hypotenuse of 29. And how far I've traveled west, well, for this one, we would use cosine, wouldn't we? Because this is the leg adjacent. Cosine of 28 degrees equals how far we've traveled west over 29. You can figure out the rest. I'm just going to set these up. If that makes sense. We won't spend all our time doing the calculation. The tough part is usually figuring out how to set it up. An airplane leaves an airport and travels due east. Okay. So if I look at my east-west grid, travels due east for 255 miles. Okay, so it started at the origin, now it's here. That's 255 miles away. Then it heads due south. All right, we know what that means. Going down here for 330 miles. From its current position, along what heading should it travel to reach the airport? And they should say how far is it to the airport. So the distance I'm interested in is right here. That's how far. And the other thing we're interested in, let me get it back to the airport there. So we want to know this. This is our hypotenuse, or sometimes we think about this as radius. And this is a right angle, clearly, because this was east and this was west. Well, when it's going back, this becomes the from. Okay, so let's draw its return. So it's going to be going from the origin, and it will have to travel, instead of east 255 miles, it will be traveling west 255 miles. And it will be traveling, instead of south, 330. Whoa. Instead of south, anybody catch that goof? Instead of south 330, it's going to be traveling north. So it'll be going north 330. 330. So in order to get back from here to the airport, we want to know how far this is, and we also want to know along what heading. So heading is this angle here, isn't it? Is that right? Let me check back. Whoop, whoop. Heading, north line in a clockwise direction. No. So all of this was good. This is 330 straight, regardless of what I've drawn. And heading is always taken from north-south and in a clockwise direction. All right, that's what we're looking for. This this angle and this distance. I'm going to change colors. All right, I don't have the hypotenuse. I don't have this angle. If I get this angle, I'll be able to figure out the rest of it. Without the hypotenuse, we know we're always going to use tangent. So the tangent of this angle here, let's call it alpha, is equal to opposite 330 over adjacent 255. Here's a case where I have the ratio and I want the angle. So what am I going to use? That's right, the inverse function, which allows me to put in this ratio, tangent ratio, and find out what that angle is. Let's pull over our calculator, put it up here, turn it on, and make sure I'm in the right mode. I want to be in degrees. You notice they don't use radians at all in these. So I want to do second function to get to arctan, and then I'll put in my ratio, 330, that's my y, divided by my x, 255. And I found out my angle is 52.31. So alpha is 52, this is a decimal, 31 degrees. If this is 52.31, and my bearing also includes another 270 degrees, right? 90, 180, 270, plus this, then for my, excuse me, I should have said heading, 270, and this will give me 0.31, 2, 2. That's right, I've almost made a complete circle here. To get to 360, I'd go right over to here, which is another way that could have been solved, by the way. Let's go back and just check out bearing. Course is my heading. So I've got my heading now. It should be 322.31 degrees. What's the next thing I need to figure out? Okay, yes. What is this distance here? And I can use this angle that I have now to figure out my hypotenuse. What would be a good way to do it? Well, I always like sine. Let's use sine. I can say the sine of, oh, I don't want to use, no. I want to use my alpha, the sine of 5.31 degrees is, okay, the sine would be 330 over my hypotenuse, which I'll call d. That's the distance I'm interested in. So d is going to equal 330 divided by whatever the sine is of this, of alpha. Turn this on. I'm going to say sine of 52.30576 equals, okay, 0.7913, 0.7913. Did say I wasn't going to solve them, and here I am solving it. Times, no, I'm actually dividing, so I need to put that as a multiplicative inverse. Whoops. Oh, no, 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 no. Clear that. I want this one. What was I going to do? Square it? Whew, that would give us a terrible answer. And then I'm going to multiply the multiplicative inverse of this times 330. The reciprocal times 3. Whoops. Forgot my times sign. I can demonstrate every possible error you might make. Okay, so 417.04 miles. 417.04 miles. I really got carried away doing this problem. I guess I got interested in it. That's a scary thing. All right, that's enough for today. You have ahead of you some more problems, and then in class, in addition to those problems we didn't finish, in this session you'll do that homework.